cover less.
Okay, hello guys, welcome back. So today we'll be doing convolutional neural networks, and let's start.
Okay, hi everyone. Welcome back to week 3 of the deep learning tutorial series. So today we'll be doing convolutional neural networks. So before I begin, I would like to say that this is more or less what sparked the deep learning revolution these days. Just to check, can you all hear me? Good. Okay, so this basically is what I would say what sparked the current AI trends. Okay, because it was an image model, namely AlexNet. Okay, on the Imagenet challenge. Okay, because it was so good, it outperformed the other competitors by like 10 percentage points or so, compared to the other traditional handcrafted methods or like probability-based methods. Yeah, this convolutional neural networks kind of revolutionized the field, and then soon after it moved on to other fields. Yeah, and then most of what you see in deep learning, actually the most use cases for deep learning comes from convolutional neural networks. Of course, now the trend has changed a little. There's transformer models, okay, but that's how the current deep learning trend has been sparked, at least in my opinion. So the topic today is a very important one, and I feel that this topic really is the core of what deep learning is right now. Okay, so this is as usual the same stuff that I talk about every week. So focus more on the concept. I'm not a math person. I prefer to step you through images and the concept. So today you will see a lot of images. Okay, so don't worry. Okay, if you don't understand anything, feel free to ask anytime. Okay, I'm okay to split this session into 2 if needed, because this session is actually quite important. Okay, so let's move to some recap from last week. Yes, so in this recap, I actually want to touch on what I covered, a bit of what I covered last week, which is the batch versus the stochastic gradient descent. Okay, last week, Chicken asked me a question, which one actually can come out of like local minima easily? And then I said batch gradient descent, but I was wrong. Actually, batch gradient descent, because it averages over the entire batch. Okay, we remember the gradient is updated only at the end of the batch for the batch gradient descent. So because of that, the gradient update will be more smooth, will be less jerky as compared to stochastic gradient descent. As you can see over here, it's like more jerky compared to batch gradient descent. Hence, stochastic gradient descent actually has an advantage of getting out of local minima more easily. So yeah, why then do people like want to use like mini batch gradient descent, right, instead of stochastic gradient descent? Because actually stochastic gradient descent, if you can use it, would actually perform the best. It converges quite quickly, and it also can get out of local minima quite easily. Okay, and actually the reason is because remember for back propagation, when you do a node to another node, like when you do a feed forward, so let's say this is your neuron, you feed forward and then go to the output, right? And then when you want to do your back propagation, actually that is like taking up another time step to back propagate through a network. So this back propagation step can actually be very costly in terms of time. So in order to use less time to run the network to train, okay, people have come up with a mini batch gradient descent, which is a compromise between like the jerkiness of stochastic, which is actually good, okay, and basically the efficiency of the update through doing a batch. Okay, because when you do a batch, you can guarantee that you will go to the minima of the entire batch. Okay, it's actually quite a good method to get to like the local minima or the global minima. Okay, so mini batch is a compromise between the going into the global minima, which is like stochastic, will do better, and basically not so frequent updates of the back propagation. Okay, so whatever you see here, normally people use mini batch gradient descent, batch size about 32. Okay, so just to clarify this, okay, because there was some misconception that I said last week. Any questions so far? Okay, if not, I will move on to today's topic. So today we'll start off with a very interesting exercise. Okay, so we will do a hands-on demonstration of what a CNN can do to classify. So I would like to invite you all to join me. It is about 10 minutes of this simulation. So click on the link here. Okay, Teachable Machine.
Could you post the
Say
link in the
again.
chat? could you post the link in the chat? We can't click on the link.
Oh, okay, sure. Yeah. Let me just stop my share and then I'll post the link there. Hang on. Yeah, so we will all go to this website. Okay, I will just teach you how to do it first. Okay, then we'll do it together. Okay, so I posted the link on the chat. Okay, so
we can see it.
okay, so this is how the site looks like. So firstly, Teachable Machine is basically you can train your own CNN with your webcam, or you can upload some files. Okay, and you can run real time, and then you can see the classification real time. It's really very cool. Okay, so for this, let me just show you how to do it. So maybe for first class, you can put yourself like person, like maybe your own face is called person. So you then click on the webcam button. You just click here. And then you press hold to record. So like you see over there, my face is there. So I can hold the record. Then you can come out with different configurations. Okay, so when you hold, you can record the whole thing. So this is like they recorded me as a person. Okay, then maybe class 2, I'll use like handphone. Okay, so handphone, how do? I have to exit the screen first. And then like maybe I put a handphone like that. Yeah, you try to put like more angles, okay, because like it's a 2D for the image. So if you rotate it, my experience is if you do some rotation in 3D, actually helps the image recognizer to recognize, because there's no way someone who only views things this direction can like extrapolate that the phone is like that. Yeah, so usually this will help with image classification. So let's do a third class. Let me just see what object I have right now. Okay, so I do have, let's see, a mouse. Okay, so I'm going to use a mouse. So let's use a mouse. Okay, and then I use my webcam again. Okay, so that's it. So now what we do is we then train the model. You don't have to use the advanced here, the batch size epoch. We can just let it be. Okay, we can just train the model here. Okay, so let's train the model. Let's click on the train button. Okay, so you will train in real time. Okay, and then, oh, you see the model is trained. All right, so let's take a look at how this classifies. So now it classifies, you can see now that it classifies as person because you see my face there. If I go away, then it will go to like either hand or mouse. So it's more handphone because I guess handphone takes more of the screen. So if I put my handphone here, it's like that. Put my mouse. So what if me and the mouse appear at the same time? So I'm more dominant, right? If I put my mouse here, yeah. So you can see the output probabilities at the bottom here. Yeah. Okay. So do try it out. Actually, I would like to invite you all to like share what you have tried out also if you are trying out different things. Yeah. So yeah, maybe we just pause here for about 1 to 2 minutes, let you train your own model. Try it out because actually this is really very cool. It actually uses train weights of a larger model, and then you can just apply it using transfer learning to classify our pictures. That's why it can classify so well and so fast. Okay, so that's very cool. We can even add more classes. The more classes you add, the harder it is to predict. Okay, especially if the classes are very similar. So let me just add a class to just test the model's capabilities. Okay, so we can add another class called person without spectacles. Okay, so I'm going to take off my spectacles and then we'll see whether it can classify me without the spectacles. So this is a harder thing to classify, okay, because specs is a bit. So let me just try. So you see, there's no difference between my face with or without the specs. Let's see whether this can classify me without the specs. Okay, so I've done that. And let's try to train the model again. Yeah, and then we see whether it can actually, perform the inference as required. Okay, so now it requires a little bit more time to train because there's more samples to train. Yeah, so do try it out. Okay, if you are willing to show what you have shared, what you have trained, we can also ask you to share screen. Okay, so we can see that it's now classifying me as a person. I take off my specs, and immediately you see that it classifies person without specs in all angles. If I go further away, put my handphone up, the handphone, put together is like a person, yeah. Mouse, how about a mouse? How about if I put both together? It's about handphone, right? Mouse, handphone. Still mouse. Okay. So apparently it looks like a mouse when it's not given the full frame. If I put like that, it looks like a mouse. Okay, so you can see already in this very simple example that CNNs, if you don't train it with like enough kind of examples, it is quite prone to adversarial attacks. Because you see just now my handphone, I put like that, it looks like a mouse at certain angles. Yeah, so in order to prevent that, okay, there's a need to train with more models. Train with more data, train with more classes. Okay, in order to like sort of differentiate between the classes better. So in general, if you want it to detect more fine-grained differences, like for example, specs and without specs, you need to train it with those two classes, okay, for the model to learn the difference between those classes. Okay, like if you want to train a classifier to classify someone with hair or without hair, the same thing. Because if not, it will just, the features that it extracts, it may not be as good as what you want. Okay, so for your use case, you need to really think what you want. So if people want to classify deepfakes, then for the samples, you need to have a real person and a deepfake sample. And then they can sort of classify deepfakes, which actually can be quite obvious to a computer. Because you all know about deepfakes? Anyone? Have you heard about it? Deepfakes, where you use like a famous person like Obama or Einstein. You train your own face on it, then you can like use it, your expressions on that person. Yeah, so actually there's quite a lot of users for CNN-based models. That one, they use GANs, generative adversarial networks. Yeah. So those kind of things, if you want to make the model classify better, then you will need to have the right examples for the different classes so you can learn to differentiate better. So I'm just sharing some ramblings here.
I have a question.
Yes, come, go ahead.
So for you said this model can be done so quickly because it's not actually done from scratch. There is transfer learning, right?
Yes.
So can I ask, are there some pre-trained models which are better at doing something like faces, and some models which are doing something better, that they have been trained to do something better, like classify different cats? Is that the case, or is it that if you train a good model, it can do almost any kind of image classification?
That's a good question. So actually, how well a model performs, as what I said earlier, depends a lot on the data set that you feed it in and the different classes. So the top performing models so far, I mean, not so recently, but just last year, the top performing models use Imagenet, okay, which is maybe I can just show you what Imagenet looks like. So typically people use Imagenet, and Imagenet is basically a database, okay, that contains like about 1,000 classes, okay, and basically these classes involve like a few different classes of animals, so they can classify animals pretty well. Humans actually not too many classes, okay. I don't think there's much. Okay, they don't have the classification here, but yeah, so most models trained on ImageNet tend to be quite good with like animals because there's really a lot of animals. Yeah, you can see like horned viper and stuff. So if you want to do like face analysis, you probably need to train on your own data set that contains different faces and everything. Okay, because you can see over here, this more animal related. There's also cars and stuff like that. So ImageNet was the go-to standard for like the last 10 years or so. Okay, but recently there's a bigger data set that came out from Microsoft. It's called JPT300. Maybe I can just show you here, JPT300. It's used in vision transformers. So this one really, they just eclipse ImageNet by about 800 times. And basically this data set is, so a lot of the models that are trained are currently using ImageNet, and I think they are sufficient for most purposes. But if you want more in-depth models, like models that can actually look at like whether you have a fake eyebrow or not, you probably need your own data set for that. But I would say that in general, the features learned from ImageNet are quite robust because there's so many classes there. It really learned quite a lot of things. Did that answer your question?
Yes, thank you.
Yeah, so I think in deep learning in the future, okay, for most applications, if it is image related, it will probably have to be someone has already trained a very big model on a huge data set like this JFT 300M. Oh, it's not JPT, JFT 300M. Yeah. Basically, you train on this very large data. And then what you will do is then you take the model weights and then you add in one last layer or add in a few more layers to fine tune on your own data set. So that is the current trend that we are at in deep learning, because it is just too expensive to train from scratch for all the use cases that you want, like cats versus dog, you train the cats and dogs, or person versus mouse, you train another data set. Yeah, so this can be quite time consuming, and you might learn the wrong features because of the amount of data you use is too little. You may not learn the right features. So the trend so far is use a large data set and then you fine tune on whatever use case you have. Yeah, same thing applies for video classification, because video is basically just made up of multiple images stringed together. Okay, I hope that was fun. Anyone want to share what you have classified? Just a shout out, okay, using the Teachable Machine. If you like to share like what classes you have made, feel free to share. Okay, I mean, feel free to put in the chat if you want to share. If not, maybe I'll just wait here for half a minute to 1 minute for any further questions on this. I like to keep the introduction a bit more exciting, okay, because I quite like this area of deep learning. I hope you like it too. This is the trending thing right now.
Can I ask a technical question? So,
okay.
Feel free to post anything you have on the chat. We'll have a look at it. But my question is, when you take something like Imagenet or the new Microsoft Net, how many layers are you actually taking from them? Because I suppose that you need to take.
Oh, sorry, it's a Google dataset. Sorry, just
sorry, Google. Okay.
Yeah, it's a Google dataset. Yeah.
Okay.
Yeah.
So they pre-train their model, and you're taking all the nodes, or are you taking just some?
So usually when you do transfer learning, let me just see if I can Google for you this. I don't have a slide on transfer learning, but usually what you do is you just replace the last layer with
with the classification layer.
Yeah. For example, you can look at this. Like this front part here is all the same, and the back part you just change the last few layers, like some linear layers also.
Oh, so you're copying the
entire
part
thing, and then you can freeze the weights. So depends on the kind of data you have. If you have a lot of data to train from, you can let the model go free, unfreeze all the weights and train with your new data. But if you have very little data, you want to keep the feature layer. Okay, you want to keep these layers here, which are the feature layers that are trained usually. Then you freeze all the weights here. So you can choose to freeze all these weights, and then you just focus your efforts on the last few layers. Yeah, if you have fewer data, you just train fewer layers, which makes sense. Yeah, so it can really be defined quite dynamically. Now, if you are interested, I can have another session on transfer learning. It is very important actually, because transfer learning.
I think that the transfer learning method will be very, very useful for businesses, because first of all, you don't have to architecture the whole first part. So that's one. And you don't need to have the data set. That's two. And then you don't need to train. That's three.
So you need the data set you want
that do you want, but I mean,
but you don't need so many samples.
Yeah,
so you see just now when I did my teachable machine learning, if I were to do it from scratch, you will need to see me have 200 over image samples for each class. But you see, in fact, I just do one image sample is also fine. You can also learn, because the features are not learned from all these images. These are just like fine tuning. The image features are already learned from pre-existing data set like Imagenet.
Do you all ever worry that the image that is pre-trained on is a bit biased to certain
yeah, of course. There have been studies to show that there's more whites than blacks. If I'm not wrong, okay, don't quote me on this, okay? I haven't really done much research on this, but there have been a certain bias in the representation of the ethnicity of the people that were used in the training. So, I mean, there are some people who show that, regardless of their ethnicity, like Jamaican or what, the model just classify them as blacks.
Yeah, this is the question actually. It's one of the chat questions, does ethnicity influence the facial recognition? So that's what you're talking about, right?
Right. So the answer is yes. Okay. So deep learning, being a data-driven model, depends heavily on the data you use. Okay, that's why it's so useful, and that's also why it's so dangerous. Okay, it's useful because you don't have to define handcrafted rules, unlike in the past where you need to do like if man is greater than 150 cm, then you look if the eyes are blue color. You do if else, you can do a huge tree of rules. Okay, but with deep learning, you can abstract it all out in the neural network. You can just give it the data and it will learn the sort of implicit rules automatically. But it can learn rules that inherit the biases that are present in our data. So, people are not perfect. People have biases. So these biases can actually go into the model if you use the data set, especially if you use like misrepresented or an imbalanced data set with not equal representation, then you have these issues. Like in the US judiciary system, there's been a model that's trained to like predict whether someone will re-offend or not. So it's been found out that like actually they predict blacks to re-offend much more. Okay, given the same kind of background and crime, you put in the model, just put their ethnicity as black compared to whites. Okay, and the chance of re-offending will be much higher by that model. And that's actually not the model's fault, That's because the judges in the data set that they give, and also because of how the past trends have been, it is that case, okay, that blacks have been persecuted more than whites. Okay, so, what is fairness, right? So, yeah, I mean, usually for when people do the decision, we will we'll leave the judgment based on expertise. Okay, but if you let the machine do the system, then people are more curious whether the machine is it biased or not. But actually the bias might come from the data, and the data is actually driven by humans. So long story short, humans are biased, but we don't want our machines to be biased. Okay, so there's differing standards here. Okay, Kaichi asked a question. Is there a standard usually as to how many layers you should make in the model for it to be optimal? Sorry, I don't quite understand this question. Like, what do you mean by that? How many layers should you make? You mean how many layers should the model contain? Is it in the base? No, there isn't. So it depends on your use case. Again, you have to calibrate based on what you need. If you just need a classifier model, actually you don't need that many layers. But if you need to do like object segmentation to segment out where the face is, or where the eye is, where the nose is, then you will need more layers. And the kinds of layers you need will be different. Okay, because like some you need to map back to pixel space, some you go back to the classification space. So that itself is actually an art to discover what are the structures needed, and it's an active area of research actually. So most of the models that you use right now for different use cases actually come from some research paper somewhere that a lot of groups have tried different models and methods to perform well on the data sets, and the better performing methods are usually the ones that are adopted in industry as well. So yeah, you can also, that's why industry does a lot of deep learning research as well to find out what are the optimal architectures to use. But for starters, using CNNs, ResNets, or variants of CNNs, and now is transformers. Using some variant of this should be quite competitive as a baseline. Okay. So last call. Anyone want to share your teachable machine learning? Okay, if not, I will stop my share here. Okay, I will want to go back to my slides. So I hope this has given quite a good introduction to what the CNNs can do. Okay, it's one of my favorite architectures. So I don't mind splitting this session into two, just to cover it more in detail. Okay. All right. So let's see. Teji, you asked a question. Can we detect multiple objects at the same time from one object? For example, detecting multiple persons by training on one person. The answer is yes. So actually, there's this model called object detection. Okay, that uses some way of like basically instead of just okay. So this one is I did prepare a slide on that, but basically the idea is you train on Imagenet. Okay, you already can recognize all the different classes. Then what you need to do is to give bounding box proposals to the network, and then they will classify each bounding box according to like how confident they predict the class to be. Then after that, what they do this method called non-maximal suppression to choose the bounding box that gives you the best fit. And then all the not so good fit, they just eliminate. Then based on the output of that model, you can have various bounding boxes. And then these bounding boxes can detect like 2 people, 3 people, 4 people. Yeah, in fact, if you want the model to count the number of people, you can just simply count the number of bounding boxes for that class. Yeah, so yes, you can do it. Yeah, you can even do pixel level segmentation to determine where the people is, where the cat is. Yeah, so all this have been done already. Yeah, for more details on all this, I would like to refer you to this paper called YOLO, Y-O-L-O. Okay, YOLO, and let me just type it here. YOLO, Y-O-L-O, or maybe I just put on the screen, okay? There are some papers that do all this kind of object detection, which actually have been quite good. Okay, so there's models like YOLO, you only look once, faster RCNN. Yeah, so these are the kind of models that are typically used for object detection. You can take a look at those if you're interested. Okay, so but for today, we'll be just going through like really the basics. We'll be going through object classification. Okay, to just give you a flavor of what the network can do. Okay, any questions before I move on with the with all the technical details of how the CNN works?
This is Jeremy. I was just looking through the NIST website for facial recognition, right? That they do a ranking every year. So for the top 10 facial recognition companies, do they really differ only because of how they tweak their parameters, their accuracy, and so on and so forth? Is that one of the only ways to determine whether you're...
I mean, it's hard to give you an answer here because tweaking the parameters, you mean parameters of the model, is it?
Yeah.
Yeah.
I mean if they're all using CNN, right? So
yeah, but the data set, are they using the same data set?
Yes and no, depending. But I know NIST has a standardized. Yeah.
So it's both ways, you see. The data set is important. The model is also important. So your data set, I have realized in my experiments with CNN, that the augmentation of your data set is very important. So like, for example, I have this data set called CIFAR. It's like the mini images data set. There's like a mini version of Imagenet. Okay, so in CIFAR, if we just augment the data a bit by doing some rotation, doing some image translation, flipping, you can up 10 percentage points just by data augmentation of your training of your test accuracy. Okay, and that shows how important the data is. Okay, because with all this like a little rotation, a little translation, you can actually give the model more examples and it can classify better. Okay, so that is something that that is important. The model itself is important, as we will look at today as well. In the notebook as well, the model itself is very important because the model can then choose how much you can capture with your data. Okay, maybe I just draw the pipeline for you here. Okay, so I just draw on the left here. Okay, so we have this thing called the data. So the data contains a lot of information. Okay, and actually the data alone can determine how good a model can be. Okay, that's why a lot of people have done work on like increasing the data size. Okay, but the data size can be increased, but your model, if your model has not enough of the right representation to learn the data, a lot of the information from the data will be lost. Okay, so the deep learning pipeline depends heavily on both the data and the model itself. Okay, being a data-driven kind of pipeline, you need to have all this quite well established. If not, you will lose information bits and pieces. So you can treat of it as an information pipeline. Your data is always the most informative. Okay, then you want to extract out more information, like you want to use if-else statements or use some version of filtering or like basically different ways of processing different data. That's through your model. So then you try to put the information into a format that will actually sort of be more useful for your end product. Okay, so there's very important interactions between your model and your data, and all this will affect your output. So your information will have to flow through it. So if you view it from an information kind of perspective, actually the more you process your data, the more information you lose. Okay, that is actually from information theory. Okay, because you can never get more information than what your initial information is, which your initial data is. But you cannot just plug the initial data into your output because you cannot get a plausible output for your use case. You need to process it to get a plausible output. Take for example, if you want to detect my face, I can give you all the pixels. Inside the pixels confirm, you can find out that something correlates to my face. But is it useful? It's very difficult to use the original pixel information to find out whether or not a face is there. So you need to have some way of processing, and that way of processing it can be like detecting where the two eyes, the nose, and the mouth is. Okay, and that can be done using CNNs. Okay, so this way of processing it, you can either use like traditional methods, which is really you detect where the eye is, you get where the nose is based on generic shapes, and then you try to piece together the face. Okay, or you can use deep learning, which is preferred because deep learning you don't have to learn, you don't have to handcraft the rules at all. The data will tell you the rules. And yeah, I hope this is a very important question actually. Deep learning is really based on data, and the model is important because you need to use that model to process the data in the right way. That is why, okay, later I will touch on a bit more why CNNs are important, because CNNs actually process the data the right way for images. Okay, in order to extract out the right information, the CNN has the right structure to take out the information. Yeah, okay, I would like to end the response here. Jeremy, did that answer your question?
Yeah, thanks a lot.
Yeah, no worries. Okay, yeah. So I'm gonna move on to like what this CNN is. Okay, I probably will want to split this session into two because there's a lot of important juice here. Okay, I think this is more important than RNNs, to be honest. So RNN, maybe you can do a small section at the end, but CNNs really is the focus. Okay, CNNs, then perhaps next time I can teach you all transformers. Okay, because I think these are the two key things driving deep learning right now. Okay, so for CNN, just now you saw the teachable machine learning. Okay, they use this architecture called MobileNet. So you can see this architecture. I will not be covering MobileNet today. Okay, but you just need to know that it uses convolutional neural networks. Okay, so this is how it looks like. Okay, if you're interested, go to the Medium article to see like what is done. Okay, but for today, you will learn certain concepts that can help you understand better how this kind of network is used. Okay, MobileNet is used because MobileNet is a network, okay, that can actually perform much faster inference timings, okay, because they use this depth-wise separable convolution, which has fewer parameters and it runs faster. So MobileNet is like the go-to standard for like edge applications. Yeah, that's why people use MobileNet for this. Okay, so now we move on to the main thing. Okay, so why CNNs? Why are CNNs so useful? Okay, so if the data allows us to use the same structure in multiple parts of the network, same structure in multiple parts, okay, then can we use the same structure and then learn once and apply all instead of learning from scratch all the different parts one by one, right? Can we just learn this way of processing and then apply it to all the different things that we want to apply it on? So you like sort of like, you can think of it as a modularized structure. So you want to learn something that can process things in a certain way. Okay. Oops, sorry. What if you also want to have only connections in a local neighborhood? So, okay, you see in what we learned in the last few weeks, we learned multi-layer perceptron, right? We learned multi-layer perceptron, and this multi-layer perceptron has connections that basically go everywhere. Okay, it connects fully. So from your previous layer, you have weights leading all the way to your next layer. Okay, and you know what? This is actually not a very good structure. Researchers have realized. Okay, why? Why is it not that great a structure? Because sometimes there's no input-output relation between the middle nodes and the next layer. So by putting like a connection there, you are actually telling the network, okay, there's some relation there, find it. Okay, but actually what if the answer is that there's no relation at all? I can just erase this line here. So by putting a link there, doesn't mean more links are good. By putting a link there, we are actually making the network more confused because sometimes some input is like garbage. Okay, it doesn't really affect, it's not related to what you want. Okay, I mean, you can think of something like, if you have a certain text like this, like maybe you like, I like CNNs. Okay, imagine you have a certain text like this. Can you see my text, by the way? Yeah, so imagine you have a certain text like that. Okay, what if in the middle I have a lot of garbage? Like, yeah, so does it mean that more information is good? So if you give it more, I'm just using a simple analogy. If you give the network more information, you see, you sometimes cannot ignore. So here I just need to find I like CNNs, right? You need to actually like sort of like cancel out this one. Yeah, but if you just do like a fully connected network, it's like giving the network all the data and then asking the network, nah, here's this stack of tutorials, or here's this stack of data, go figure. Yeah, of course the network is sometimes not that smart. It cannot figure out what to do all the time. Okay, so fully connected networks may have this issue where you just give too much information to the next layer. So what if we just need to have only certain connections that are important, and we already know beforehand that they are important because our data tells us it's like that. The structure of the data is just like that. Okay, so will it be better to just train that same structure once and use it many times? Okay, of course the answer is yes. Okay, I spent so much time saying this is yes. Okay, why is this important here? Okay, why? Okay, firstly, let me just share with you what a CNN roughly would be if we just modify our MLP to a CNN. What will happen is that we will have this line here. Okay, this is the weight. So maybe this weight is like 0.1 from the right node. Then all of the processing to the next layer will have weights of 0.1 to the next node like that. Okay, it's very important because this weights of 0.1 to the next node, okay, means that it's something like an image. Okay, so let's say if you have an image, okay, that you has only 2 pixels, okay, and then like maybe you are just seeing whether or not like you just want to find out whether the right pixel is like maybe greater than the left pixels in terms of color intensity. So you can just like take a look at these 2 pixels like that, apply maybe a weight of 0.1 to the right pixel, and then maybe at the left pixel, what can you do? You can apply a weight of minus 0.1. Okay, then in that case, it's like a simple network to just compare the left and the right pixel to see what is the difference between the 2 pixels. I mean, sometimes you might want to like use this to like classify in terms of like ages and stuff like that. So you can use this kind of simple, I mean, here's of course very, very simplistic. We just only have two inputs that we want to compare to. So if you're just only interested, your use case only needs you to find out whether or not the right pixel is of a greater intensity than the left pixel. Do you need to have all the connections from all the left and right pixels, and including all the other pixels here? Do you need to have this information? Yes or no? Do you think if I just want to focus on this left and right pixel, which one is more intense? Do I need to have all the pixels in the network? Yes or no? Anyone?
No.
No. Very good. Yeah, whoever answered no. Yeah, so that is exactly why we use like CNNs to constrain our neighborhood of where we look at, okay, in order to extract the right information and not confuse the network with redundant information. Okay, I hope that this is clear, okay, because the rationale behind using this way of doing things is the foundation of many deep learning methods. Okay, it is even more foundational than MLPs actually. MLP is a long time ago, people have this perceptron model, okay, and then they just build on many layers from it, but it didn't work too well for most use cases. The true revolution came when people realized you can do CNN-like architectures, and then that's when deep learning sprouted. So I hope you have an appreciation of this. So you can see that like this block in purple here is repeated throughout the network. We apply the same lens, okay, to view our pixels. So I mean, if you look at this nodes as pixels, you can see that we apply the same lens to view it. So it is like sort of having something to like filter our vision, right? So people call them filters. Okay, this repeated block that we use to visualize the data, people call them filters. or in the old computer vision term, people call them kernels. Okay, I personally like to call them filters, but I call interchangeably now kernel or filter. So this repeated block used to analyze your input data is called a filter or a kernel. Okay, for today's and the subsequent subsequent slides that I'll be showing. Okay, questions? Okay, very good. So stay tuned. Okay, now I'll show you how a CNN looks like. Okay, so remember this slide in the first lecture I showed. So we have an image here. Image goes through convolution and then ReLU. Okay, and then after that it goes through like pooling. Okay, and so this convolution and ReLU is basically using the lens that I was talking about. You use a fixed filter to sort of analyze the different patches of your image. Okay, and then after that you do pooling. So I haven't touched on pooling yet. Pooling is a way to reduce the dimensions of your output. Okay, why pooling? Okay, pooling has two uses. One is to help to make it more generic, because you can have a different kind of input mapping to the same output, so it helps with generalization. I'll cover more on that later. Second use is because deep learning networks are just too huge. If you were to use the original filter size or the original output size in the next few layers, you realize that it compounds. The more layers you have at the beginning, the more parameters you have at the end. So that there needs to be a way to sort of like reduce the number of parameters so that it doesn't explode too much towards the end. So people introduce pooling. Okay, then you repeat this architecture, convolution, filter plus pooling. You repeat all the way to the end. Okay, so whatever you see here, this is a CNN. Okay, how does CNN relate to MLP, you ask, right? So typically in the CNN part, the last few layers will be an MLP if you are doing like classification, because you still need to go to like the few classes. So in between the CNN and the MLP layer, okay, the link bridge between them, okay, is typically this layer called the flattened layer. As I highlight over here, this is the flattened layer, which basically just flattens my CNN structure into one line again, like one linear line. And then you can proceed to apply whatever we learned in the past few weeks, which is called the MLP, okay, in order to do your classification. Okay, so this is the rough structure, the backbone of a CNN architecture. Okay, I hope that's clear. Just feel free to interrupt me anytime if you would like to ask anything. Okay, no, I treat it as you can understand this. Okay, so now we come to the first technical detail. So the first technical detail that I'm going to share with you today is called the convolution. Okay, so for those who know like engineering, convolution actually means taking the integration of original item and the convolve version, which is like more or less the flip version of the filter, and then you like integrate them together. Okay, but for deep learning, you don't have to think of it in such terms. You don't have to flip the filter. Let me tell you the deep learning method of convolution. Okay, what is a convolution? Okay, a convolution is basically you have a certain array of weights. Like in this thing here, this red color is your weights. So you can see that as we go through the image, we look at this filter size of 3 by 3, and then we just basically, you think of it like, okay, how do I do it? You think of it like you are playing peekaboo or you are playing some like hide and seek. You cover your eye like that. Okay, so you can only see this certain area in front of you. Then you shift it here, then you shift it here, and so on. So your field of vision is only within your hands over here. So you can only see a very, very tiny section of it. And then you need to sort of make sense of what you see in that tiny section. But you're allowed to turn your head. You're allowed to turn your head and view it and pick at the entire image. Okay, but you only can pick at it like bits and pieces. Each time you pick at it, you only can pick at it at a very small scale. So that's exactly what your filter is doing. You are picking at the image at a very, very small scale. In this case, it's a 3 by 3 scale. Okay, and then we need to figure out how to process that image that you picked at. Okay, and that is where convolution comes in. How do we process that part that you pick at? You typically just take whatever image here. In this case, your pixels like either 1 or 0. You then multiply by your filter, which is like this times 1 times 0. Okay, let me just go to the next slide, okay, where we have the GIF that stops running so you can see it. So, okay, let's just look at this. I draw your attention to this part here. Wait, where's my drawing? Oh, it's in green. Okay, so just take a look at this part here. So my original image, okay, has this 1, 1, 1, 1, 1, 0, 1, 0, 0. At that particular point that I pick at, it has this structure. Okay, but then in my lens, you can treat it as my spectacles. In my lens that I see things in, okay, I'm already sort of biased towards a certain way of seeing things. How am I biased? I'm biased to see things in this way. I only see this, I only see this left pixel here. I see the top right pixel. I see the middle pixel. I see the bottom left pixel. And I see the bottom right pixel. So I'm already biased to see things in a certain way. I'm biased to see the pixels in this X formation. Okay, and because of that, okay, this filter is actually, if you think of it, this filter is actually the X filter. It sort of like figure out where the X is. Okay, because of the way the filter works, you are trying to find out where all my X's are. Because if you sum up all this, this will give you like the highest sum. Okay, so if you look at this filter here, how do we then convolve it? We just take simply 1 times 1 plus 1 times 0 plus 1 times 1 plus 1 times 0 plus 1 times 1 plus 0 times 0 plus 1 times 1 plus 0 times 0 plus 0 times 1. There we go. Okay, congratulations, you have learned convolution. Okay, this is usually done with a lot more math. Okay, but I hope you can understand from this diagram, because I think it should be sufficient. Okay, so you can see over here, if we take the sum of this, what do we get? We get 4. Okay, so just take a look at the convolve feature here. Can you tell me which of the stuff that we pick at are X's? Anyone can tell me? Where are the X's in the original image? Are there even X's at all in the original image based on whatever features that you have? Anyone can tell me? Are there any X in the image? Yep, so I just give you a while to process, because you can see that the filter here tries to find out where the X part of the image is because of the way that the filter is described. Like it has all the ones over here. So just one, it's just yes or no. I mean, you can just try. Do you think there's any X in terms of X like that in the image itself? Yeah, so yeah, just pause a while for you all to think about it. Do you think that there is any of these features that you can find in the original image? Okay, I think I'll just move. Okay, let's see. No X. Okay, thank you for thanks. So that's right. So this filter, the convolve features, you can see that it's up to 4 only. If there's really an X in the original image, it will be 5. Okay, so there isn't any over here, and this means that actually there isn't that feature in the image. Okay, so this could be a filter that will detect all the X's. Okay, and typically what we can do is we can add a bias term here in order to, like, imagine you do a -5 over here. If you have a bias term that has a -5, so what this means is that, okay, maybe not -5, -4. If your bias is -4, what this means is that you will only trigger the activation if your X is fulfilled. If you have X that makes the summation go beyond 5, 5 minus 4 is 1. And then if we apply the ReLU filter, okay, you all know the ReLU filter? If we apply the ReLU filter like this, and the ReLU filter has activation of 0, and then here will be just a linear X. So if we apply the ReLU filter, you can then see that effectively what my filter is doing is actually to just like search for the necessary filters, necessary features in my earlier feature map, in my earlier image, or it can be a feature maps. And then you can then search for where the X's are. And wherever there's an X, your feature space, your result of applying the filter will be a 5. And then once you do a bias of -4, apply the ReLU activation. Okay, you will then get your output feature. Over here, my output feature, if we apply a bias of 4, we will get, actually, we won't get anything. Okay, because over here we have no x's at all. Okay, so we will get like 0, 0, 0. After we apply the bias to the filter, and then we add in the ReLU activation, we will get 0, 0, 0, 0, 0, 0. Okay, but what if I tell you that I can change this to 1? And then I make this 5. Okay, then we will get 1 over here. Okay, because after we -4, we get 1. So this can tell us like where the x's are. Yeah, so if we do it, yeah. Right, so as shared on the chat, ReLU activates only when the output of the activation is positive. Okay, so overall what this shows is that we actually have a shared weights via convolution with the filters across positions of an image. Okay, it's because I apply the same filter across different sections of the image that I get I use the same method of processing regardless of where I am in the image. And that will give me the feature maps that we see on the right. And then this filter weights, you can actually view it as encoding a feature. So in this case, the feature that it encodes is the X feature to find out where the X's are in the image. Okay, so as this is an important slide, I'd like to pause here for a while in case anyone has any questions to ask with regards to convolution and filters. Okay, because this is actually the crux of a CNN. Okay, understanding this, you more or less understand a CNN.
Teacher, I do have a question. Just very quickly. So in multi-layer perceptron, when you backpropagate, the weights and bias change. But for this one, you don't want it to change because you want to maintain the X, right? Is that correct?
Yes. Sorry, which weights do you mean? You mean the weights here, is it?
That's right, the X.
Or these are not weights. These
Okay.
are the outputs from the previous layers, or in this case, this is the input layer. So always when you apply your filters, you are applying it on the outputs, which are not weights. So this part here, it wouldn't change when you do like backpropagation, but because when you do feed forward, if this is an intermediate layer, the output activations can be based on the earlier few layers, which can change if you update the weights of your filters.
Right, but the convolution square times 1 times 0 times 1 times 0 times 1, this does not change, right? This filter.
Okay. So the filter, as in these values here, right?
Yes, that's right.
This can be changed by backpropagation. So all these things can change by backpropagation, and not just this. There's also a bias term that is not shown here. The bias can also be changed by backpropagation as well. So all these are trainable parameters that the model has.
So doesn't that mean that every pass and back and pass and back, this doesn't always look for an X? Sometimes it looks for maybe a line or a horizontal line or a vertical line, and it finds the best filter, like the best matrix of multiplication for the filter. Is that right?
Yes, you're right. So essentially what this shows is that our feature, what we are looking for, in this case, we are looking for an X. But if let's say the data doesn't need an X, if let's say the data doesn't need an X, then it can look for maybe a line instead. So these are called dynamic filters. It changes. So initially it can be an X, but if let's say the image doesn't need an X, maybe the image needs to find out whether there's a U shape like that. It can slowly evolve to be a U shape. Yeah, so that's why it's so powerful. Because if you give enough starting filters, okay, and you let each of them evolve its own way, soon it can evolve to find the feature that's important for classification. Like, if let's say you're talking about MNIST, okay, like MNIST is the digits data set. If let's say you want to classify like a number 1, I mean, the surefire way to classify number 1, right? Okay, is actually to look at whether there's a straight line. Because I mean, it's more or less the only number with a straight line like that. So if let's say this is important for 1, soon one of the edges will correspond to finding this straight line, which indeed is the case. I mean, you can also find the horizontal line here also. Yeah. So yeah, this is the beauty of CNNs. You can actually have the filters find the right data. Imagine if you were to have to do this problem yourself. To, like, for example, I use digits because it's, I use digits because it's easier to explain. Okay, imagine if you have another digit here, like the digit 6. Okay, let's say I want you to find out how to classify 6. How will you specify the machine to classify it? Like if using like if-else statements, like compared to the other numbers. I can draw the other numbers here. How can you differentiate number 6 from the other numbers? Yeah, you can. I mean, you can just answer in a straightforward way, like
So
if,
no straight line first.
okay, no straight line. Okay.
One circle.
Okay.
And probably the circle being connected at one position and having a tail going upwards.
Okay. That's good. Yeah. So these are like characteristics that the filters can slowly evolve to find out. Okay, but you know, some people write 6 also, they write in some very weird way. They write like this. Yeah, so based on that, like we can then adjust the different features accordingly to identify some of these quirks. Okay, so that's why the number of filters are important. Then you can identify more features with regards to the initial input image. Yeah. So yeah, Chicken, did I answer your question?
Yeah, that answered my question. I guess that's the reason why you use a dynamic filter instead of just pixelating the images. If you just want to reduce the size of the number of pixels that you want, you can just pixelate it. But this one gives a dynamic filter that can give you a better sense of what the model finds more interesting.
Correct. So it will learn from the data what are the important features to separate the different classes, or like other use cases like segmentation. You can find out what is the best feature to segment with, and then it will learn those features. Okay, I use will as a very strong word. It may learn those features, okay, because sometimes it may not converge, you see, if it doesn't go to global minima, or if your model structure is incorrect, it cannot learn the right features. So yeah, that's why models come in hand. So I've been doing some work on generalization recently, and CNNs, okay, it can generalize very well because of these ideas of filters. Because if let's say you can already identify where the X is, regardless where the X appears on your image, be it top left, top right, bottom left, or bottom right, you can still identify where the X is. And then if let's say your next few layers just determine on whether there's an X activated, then you classify it to be a certain class like X. Yeah, then this will mean that if you have only one sample with the X at the top left, it can generalize to those unseen samples where the X is at the top right, bottom left, bottom right. So this generalization is inherent in the structure of this CNN. Okay, but of course, it with great generalizability in terms of, so people call this idea is called translational invariance. Okay, it means that no matter where the that patch appears in the image, I process it the same way. So CNNs have this translational invariance. Okay, but of course, with this generalization comes, of course, a drawback. Okay, it cannot unlearn this bias. So it has been sort of tainted with this bias. And if your data doesn't conform, so if you give it a data where, you know, this part here, and actually maybe this part here is important, a CNN cannot learn that easily, because it has been trained to only look at this small little area. If you want it to like also link to here, it will require quite a bit of effort, okay, for the CNN to unlearn the bias of only looking at the nearby pixels. Yeah, so that's something a bit more advanced, but I'm just sharing with you because this is something that people are looking into right now. They are trying to find out ways, okay, to make the model more generic, more generalizable. Okay, But the fact is, I mean, after I did some research on it, the fact is the more generalizable your model is, the more of these assumptions that you need to make with your data. Okay, why CNNs are so useful? Because for image data, if you realize, like whatever Chicken was saying about the number just now, whatever image data you have, you can actually just start from a very, very small point here. And then after that, you can look at its neighbors like that. And then you can look at its neighbors like that. So you can actually just like zoom out. Imagine a camera, you zoom from like one point and then you zoom out and you see the whole thing. You can actually analyze an image by just zooming out from it. Because pixels, if you think about it, the more important pixels are its neighbors. Like you look at my eye right now, the important pixels to my eye is probably my the skin below my eye and the skin above and the skin to the left and the right. Okay, you don't really need to look at my eye and then zoom out to my mouth. Not so fast. You can zoom out slowly. Then you zoom out, see my nose. Then you zoom out, see my mouth. And then from there, you can classify that this is a face. So you can see that CNNs, they inbuilt this bias that only the neighboring pixels are important. Okay, and from this bias, they can build on with subsequent layers to look at bigger and bigger, they call it receptive fields. And that's why CNNs are so successful, okay? Because we can generalize from the bottom layer to the middle layer to the top layer and so on. Okay, I'm moving on. Okay, and last call for questions. Now, don't worry about asking more questions because actually I'm prepared to spend more time on this topic. It's an important topic. Okay. Okay, so I move on to traditional kernels and filters. So in this traditional kernel and filter, we do have certain things. Okay, so you look at the left, this is our original image. Okay, and what people have found out through decades of computer vision is that there are certain ways to like make the features sharper. So like over here, we can actually do like, you take the neighboring pixel, okay, and then you do a -1, means you like subtract the edges. So if you look at like maybe this eye over here, you subtract the pixels at the top, left, right, bottom, and then you amplify this pixel here. Okay, what this happens is you can see that the edges are more crisp. You can see the outline is higher. So this sharpens the image. So in your traditional like DSLR camera, they might apply these filters to make your image more sharp also. All these are traditional algorithms that can be applied without deep learning. You can also make it blur using this box blur by letting it take into account of all the neighboring pixels around it, sum up all the intensity, and then you average it. So instead of just maybe looking at the eye itself, you actually look at this rectangular patch here and then you blur it. Yeah, so this like box blur. There's also like Gaussian blur where you, instead of doing a uniform, you blur it with the middle pixel a bit more heightened. So you can see this is less blur than the box blur. So I'm not going to touch too much on all this, okay, because all these are traditional methods that are used, okay, to do like image processing. And this is actually where the CNN got, I would say this is where CNN got its idea from. You know, people don't come up with ideas like straight away from nothing. So it's based off traditional computer vision. There's this kernel, and then probably someone thought, you know, can we make it more generic? Can we make it more dynamic? And that's where CNN is born. Okay, so as I mentioned earlier, you don't have a handcrafted kernel, you learn by backpropagation. There's an additional bias term, okay, in order to, and then after you do ReLU activation, in order to tell you like which features there are in the image or in the intermediate layers. So you can think of your kernel as providing like a template. So like if you ever made cookies before, what you have like maybe a cookie template, like maybe, I don't know, for some reason you want to make triangle cookies. Okay, then you want to look at your image and see where all the triangles are. If you apply the right filter, which is like the, maybe it highlights the triangle here, like you put ones over here, and then you like put zeros at the areas outside the triangle for your filters or kernel. You then convolve it with the image. You can get maybe like all your ones here that correspond to where the triangles are. Okay, I hope this is clear. Right, I'll just touch on maybe 1 or 2 more slides, then we leave the rest for next week. Okay, I maybe just cover padding and strides and we call it a day. Okay, so for padding and strides, okay, this is basically how to convolve the filter. So how do we do the convolution? We have one method called padding and another method of stride. So what is padding? Okay, if you look at the top, okay, the top over here, there's no padding. You simply take your 3x3 filter, which is this dark blue square, and then you just go through the entire image. But with padding, you can like add zero padding. Typically, people do zero padding. Okay, you do zero padding to the outside. And then instead of starting from at the boundary here, we start at the area with the zero pad. Okay, this actually sort of like expands our field of vision. Okay, at the cost of like making it a bit more imprecise because there's this like zero values here, which is not part of the image. Okay, so this is the padding extension of your image or extension of the boundary of whatever you are doing your filter on. And the second thing we have is called the stride. Okay, what is the stride? Imagine your field of vision like this. You need to shift your point of view, right? The stride tells you how much to shift by. So if you shift by 1, I move slowly, 1 pixel at a time, like that. If I use like stride of 2, I maybe move a bit faster, like that, like that. So you can look at over here at the bottom, the filter, you can see compared to the top where it only moves 1 pixel at a time or one like square at a time, it moves 2 squares at a time, okay? And then it also jumps 2 squares at a time when it goes down. So we call this the strides 2, 2, okay? Because on the horizontal direction, so the first number is the horizontal direction, and the second number is the vertical direction. So 2, 2 means horizontal 2, vertical 2. Okay, and then we have a padding here. The padding is 1, 1. Okay, which means that 1 on the horizontal direction, and the padding is usually symmetric. So padding 1, 1 means you pad 1 on the horizontal direction, and then you also pad 1 on the vertical direction. So that's padding 1, 1. Okay, and let me just end off with the next slide to give you the math equation behind this. Okay, so the math equation behind all this padding and stride, okay, we can actually calculate what our output dimension will be. So if we look here, our output dimension, n out basically is this part here. So n out is a function of what is your input and what is your filter size and what is your strides. So this is my n in. So n out equals to n in, okay, plus 2p. P represents the convolution padding size, which is in this case is 1. So plus 2p means, sorry, I did a mistake. N in is not this one here. N in refers to your image or your intermediate layer, this blue area, what's your N in? And then over here, this is your padding. This part here, this is your padding. So N in plus 2p simply just means, if you take a look at this N in plus 2p here, maybe I use a different color. I use purple maybe. N in plus 2p signifies this entire line here. Okay, and then next what I do is I do a minus k. What is minus k? K represents the filter size. So this is k. So if I do n minus k, okay, I will basically get the amount that I need to shift my filter by. So this will give me like this green part here. Okay, and then I then divide by s. So in this case, my stride. So imagine I have a 4 here, and then my stride is 2, right? So it means that what this means is that I can move my filter twice. So it means that I can move my filter twice to cover the entire area. Okay, by this formula. I do the floor is because, like, in case that there's some extra section, we are not going to cover the extra section. We just only do like the floor, which is like the we only move it when your filter can cover the entire thing. Okay, then y plus 1. Anyone can tell me y plus 1? I mean, I have space here to move my filter twice, right? 4 divided by 2. Yeah. Okay, yep, see you there. Yeah, so plus 1 is because we do have the original input here. So this means that within this stretch of n, within my n out, from the input and the filter and the padding, you need to shift the filter 3 times in order to cover the entire length. So in this case, n in is 5. 5 plus 2p, which is 7. 7 minus k is 3, which is 4. 4 divided by 2 is 2. Then you plus 1, you get 3. So my n out is 3. Okay, so this is how we get paddings and strides. The front part here, n in is 5. Padding is 0. So k is 3. Strides is 1. So you sub in here, you get 5 plus 0 minus 3, which is 2, divided by s is 1. Okay, so the top part here, you get n out equals to 2 plus 1, which also gives you 3. Which means I need to move my filter 3 times in order to cover the entire width of my input. Apply the same analysis for the height. Okay, we will get the output size as 3 by 3 here. Okay, I will end here for today. Any questions so far? Okay, if not, for the next week, we'll cover the rest of CNNs and go through the Jupyter notebook as well. All right, thank you.